So we remain in this domain, and this time it's about the box-wing model. And the question of this project was, as Rolf explained, if we modify the box-wing model, or if we assume that we have an error in it, how would this be expressed in the global solution? I will just present you some artifacts of this project, so to say, the time you have here. So, this study was about simulating effects of erroneously modeled radiation pressure. So you see here the sun, direct solar radiation pressure, Earth, albedo. It's what we saw now 2 times more or less already. And the project was related to a subcontract with Airbus Defence and Space as part of the contract with ESA. ESA is mainly interested in the results related to Galileo. However, the results of this study are also valid for all box-wing MEO satellites, assuming an IGS style processing with it. Besides the analytical radiation pressure model the box-wing model, we also have the usual conventions that the optical properties were simplified to infrared and visual part, and to absorption, diffuse reflection, and specular reflection. And in addition, we also again used ECOM2. If one changes the area of a surface, or also its properties, this creates effects which are correlated. So this is a simulation project. We are free to adjust the box-wing model and look what happens. However, there are these correlations. So the interpretation of the simulation can get challenging, you can easily mess up. We therefore disentangle the simulations by defining single surfaces to be either fully absorbing, fully specular reflecting, or fully diffuse reflecting. We then compare large single surface pairs to, so to say, a flying point mass. This is depicted here. On the left, from an initial orbit, we do a refit of the orbit integration, estimate then the initial conditions. However, in that case here, just assuming gravitational forces and no surfaces, no interaction with radiation pressure. And then we compare it to a second simulation. We do again the refit, but this time with one surface is enabled. For example, here's the surface of the solar panels, back and front side. We also did these simulations with non-physical situations where we just simulated a single-sided surface, for example, panel front side. Since we expect these changes to be moderate to the orbit, we expect that one could also then superpose the results and also scale depending on the area. This is an overview of what all was done with this simulation project. So there was an orbit fit part, which was the blue and grayish area. And there was also a global estimation part, the green and gray area. So while the orbit fit is interesting because you can do it very fast, and you can do it in many variations. So, for example, with or without albedo to see the effects, or with and without ECOM2. On the other hand, the final goal is to see what happens with the global estimations. So, for this, with this, so to say, disentangled simulations, we started with a reference orbit with no radiation pressure, so the point mass orbit, so to say, which was created from 1 year of MGEX results, and took this point mass orbit, took the station coordinates and EOP of MGEX, and with this simulated GNSS observations, as if the satellites would be point masses. On the other hand, as an a priori, and even more modeled with the partials, also with ECOM parameters and all, we took a modified orbit. So in this case, an orbit with ECOM2 enabled, albedo enabled, and one single surface. And then in an ideal world with the global estimations, we would just get back this orbit here, and we would just get back the station coordinates we put in, but yes, we are in a global estimation, it's clear that we cannot. These things are highly correlated, such that we will have finally an effect that orbit mismodeling will leak in other parameters, like we already saw. The main results of this study are about the impact of mismodeled single optical surfaces, and from these results we also would like to mimic more general modifications, so combinations, various contributions of diffuse reflection, specular reflection, and so on, in the analytical boxing model by supposing the results for single optical surfaces. The following slides will highlight this aspect. So first of all, one question is, are we still in the linear regime? First one could think that, well, all looks linear, so to a certain extent a little bit to be expected. But if you could imagine very large surfaces, for example, square kilometer of solar panel, then it's clear that we would have a solar sail. We would be far away from a linear region. So the question is it also the case for this study that we are still linear? And this is then here with these graphics. For example, if you see here the blue point, the question is if this blue point, which was simulated with a 10 square meter solar panel, if this value is 2 times the value if you would simulate with a 5 square panel. And you can see from these graphics, if you would put a line here through these blue points and then you would go on, you would cross the 0 value. And this is just exactly one grid point further than here. So visually, at least, all these results look linear. You also see on these slides different situations. So you have panel backside, panel front side, X array surface, C surface minus, C surface plus. Here you first have the radiation pressure acting directly on these surfaces, behaves linearly because the orbit is changed only few. Then you have here what happens with the ECOM2 model, the compensation, so to say, for these modified accelerations. At least for solar panels, it compensates very well, as we know, and for the X surfaces, it compensates also quite good. But for the C surface, single C surfaces, we see that in the orbit, there we will see then an effect which would then also propagate the global estimation. This is just a reminder of the ECOM2 model, which we saw now several times. We have a twice per F cosine, twice per F term in direction of the sun, and the 1 per F term in direction D. Now, let's combine results of single simulations, single surface simulations. So, for example, here we have the solar panel, and here we have the X surface results. So, if we would now optically add up these results, is this then the same as if we would have directly simulated solar panel together with X surface? So here we have here the single simulation, single surface simulations, and here the combined simulation. And if you go then for B-dimer and read out the values and compare with this here, you would see that this holds quite well. The same situation here, center column for solar panel as C surface, and then also the same question for here, for the plus X and the C surface. Does the addition of this graphically add up to this combined simulation here? And it holds quite well. So this was for the D0 term of the ECOM2 model. The next slide is just also for the once per FB term and the twice per FD term. Here it's a little bit more difficult to see how it adds up. You really need to read out and then compare this diagram, but it also works quite well. For sure, one can do better. One can add up and subtract the result to get nice numbers. but this is just like it is now. For the solar panel, we see that there is no real effect because we do not have an influence on the BND term, which is large enough for the solar panels. So let's summarize. Analyze the impact of mismodeled individual box ring surfaces on the rate-negated orbit, so orbit fits. This was a simulation part. Also the global estimation is, so to say, simulation, but these results I did not present now. The deficiencies are absorbed by ECOM2 parameters to a large extent, and it's indeed reasonable to superpose the results of single surface modifications to mimic more complex modifications in the analytical boxing model. A corresponding paper shall follow. And as an outlook, I would like to analyze IGS final data products in order to search patterns which we saw in this study. Thank you for your attention.